This lesson is on logarithmic differentiation, and it's closely related to what we have been doing with implicit differentiation. Our steps are going to be to take the natural log of both sides of our equation, whatever those are, and we're going to move the exponents using that power rule that we learned about in some sort of algebra class, pre-calculus class, when we learned about the properties of logarithms. And then we are going to differentiate implicitly with respect to x. In other words, we're going to treat x normally and treat y like it's an explicit formula that we're just not sure what it is. So implicit differentiation, basically. Okay, so for our first example, we have like probably the most basic situation where we have y equals x to the x. And so what sets these problems apart from what we've been doing is you'll notice we have a variable in the base and in the exponent. That is how you'll know when to use logarithmic differentiation. Everything else should follow the rules that we have been learning already. So you're looking for a variable in the base and in the exponent. And so again, our first step is to natural log both sides. So I'm going to say the natural log of y equals the natural log of x to the x. So I'm just doing the same thing to both things. I'm just doing algebra right now. And then the second step is to move the exponents to the front using that power property of logarithms. So this x is going to come to the front. So I'm going to have natural log of y equals x times the natural log of x. And then I differentiate implicitly. When I do that, I'm doing both sides. The left side is going to be fairly simple. We just have to remember to do a chain rule. The right side is now a product rule where x is the first and natural log of x is the second. And that is usually what's going to happen. So natural log of y, the derivative is 1 over y, but because we're implicit differentiation here, we're going to multiply by y prime. The right side, again, is a product rule and the x's are normal. So first times the derivative of the second plus the second times the derivative of the first. Now, we are actually going to simplify and solve this for y prime. So I have 1 over y prime. Over here, these x's will cancel out. So I have 1. And then natural log of x times 1 is natural log of x. The last thing that I need to do to get the y prime by itself is multiply both sides by y. So I'm doing y times both sides, and on the right you need to make sure you do it with the whole side. So it's going to cancel here. I'm going to have y prime. On this side, I'm just going to move it to the front. Y times 1 plus natural log of x. And then finally, most of the time what you're going to see happen is we're going to replace that y with what it stands for. And our original function said that y was equal to x to the x power. So I'm going to replace that and have x to the x times 1 plus the natural log of x, which would make it easier if I needed to go to the second derivative or something like that. But this would be the final answer for right now. Okay, so now we move on to example 2. So we added a little bit more interest to it, but it's the same process. Natural log both sides. It looks a little funny on the right because you have the natural log of the natural log, but that's okay. And then move that power from being an exponent to being in the front. So x times the natural log of 3x. And again, you're going to do implicit differentiation, and the left side is going to end up pretty much like it did last time. Again, on the right, you get a product rule. It's x will be the first thing, natural log of 3x will be the second thing, and this is why we've practiced so many chain rules. So once you figure that out, you do implicit differentiation. So the derivative of natural log y is 1 over y times y prime. And then the right side is your product rule. So first, the derivative of the second will be a chain rule. So the first natural log says 1 over whatever comes after it. And then the inside derivative of natural log of 3x will be 1 over 3x. and then the derivative of 3x would be 3. So that was first derivative of the second. Then I'm going to say plus the second, which was natural log of 3x, times the derivative of the first, which is 1, because the x was just a 1x. And then again, I'm going to simplify before I try to multiply by that y. This whole first piece of that product rule is multiplied together, so I can cancel anything diagonally that's possible. So I can cancel the x that's here with the x that's down here, and I can cancel this 3 with this 3. And so that just leaves me with 1 over the natural log of 3x. And then our second piece, anything times 1 is itself, so we just have natural log of natural log 3x. And that's the most simplified that our we need to worry about with that side, excuse me. Now, I'm going to multiply both sides by y again. And make sure you keep that whole right side in parentheses when you do that. And we should cancel those y's out, and that leaves me with y prime. And again, I like to put it in the front. And everything inside the parentheses is staying the same. And then finally, our last step is to replace the y with what it stands for, and our original function was natural log 3x to the x. So our derivative is natural log of 3x to the x times 1 over natural log 3x plus the natural log of the natural log of 3x. Okay, so now we're to example 3, y equals sine x to the x. This is a good one for you to try on your own. So pause and try this problem on your own. Okay, so the steps of this were pretty similar. We natural log both sides. We move the power to the front. Again, you end up with a product rule where the x is your first piece, the natural log of sine x is your second piece. The derivative of natural log y is 1 over y times y prime. Then you have a product rule on the right. So first derivative of the second plus the second derivative of the first. Now, this one had a nice way to simplify, because if you notice, you have 1 over sine times cosine, which is cosine over sine. And that can be written as cotangent just to save some space. So hopefully you notice that. It's not a requirement that you turn it into cotangent, but it does make life look a little easier if you're working with this in a problem with more steps. So you end up with this on the right side, and then you just have to multiply by y and then replace y with the sine x to the x. Now, the last two examples that I want to show you don't fit that standard pattern. Again, like I said, most of the time when you're going to use this, it's going to be when you have a variable in the base and a variable in the exponent. And if you'll notice, example 4 only has variables in the bases, not in the exponent. But it is 3 things multiplied together. So imagine yourself trying to figure out how to do product rules inside of product rules with chain rules. It will be very long doing that, which you could do. But you learned some other properties of logarithms back in your algebra classes or a pre-calculus class that allow you to expand these a little differently. And so I'm going to start by natural logging both sides and showing you how that works. So I'm just natural logging that whole side, each side. And then this right side, I'm going to use those properties again, like I just mentioned. Whenever you have powers, they move to the front, but when you have things that are multiplied, you can separate them with logs that are added together. So in other words, I can write this side as 2 natural log of x minus 1 plus 3 natural log of x plus 1 plus 2 natural log of x minus 2. And so hopefully you remember those rules or properties of logarithms, and if you didn't, you can look those up. I have a video on that on YouTube. Okay, what that does is give us a much simpler derivative to take without product rules. So again, the left side you have 1 over y prime as your derivative. On the right side you bring down the 2. The derivative of natural log is 1 over whatever comes after it. And then the derivative of the inside in this case is just 1. So you can write that one down or not. Then I go to the next one. Bring down the 3. The derivative of natural log is 1 over whatever. And again, the derivative of the inside here is 1. And then bring down my 2. Derivative of natural log is 1 over x minus 2, and then times the 1. And that's a lot simpler than doing a product rule inside a product rule. I am going to simplify this. I can say that this is 2 over x minus 1 plus 3 over x plus 1 plus 2 over x minus 2 and clean it up a bit. I'm still going to continue this by multiplying both sides by y. So I end up with y times that whole thing. And I am going to put that back in so that I have y as the x minus 1 squared, x plus 1 cubed, x minus 2 squared. And again, this last step is a lot to write, but compared to the other option, it's really not that bad. And again, if you use the other option, they should simplify to the same thing, but this is a nicer way to get there, in my opinion. Okay, our last example again is similar to 4. This doesn't have variables in the base and the exponent like the general problems that you would normally place in this category of logarithmic differentiation do. But again, this is where the logarithm properties can help you out, so I'm throwing it in. If you looked at doing this derivative without the logarithms, you're looking at doing a quotient rule with a product rule as the derivative of the top and a product rule as the derivative of the bottom. So that would be a lot of steps inside of other steps. So again, if we natural log both sides, you can use properties of logarithms to expand and then take the derivative. So I natural log this whole side. What the property that I need you to remember now is that when something is on the bottom of the fraction, you're doing the natural log of it, you can expand those by subtracting the logs. The top is still considered positive, it's multiplication, but you're adding those. So in other words, this is going to expand to natural log of x minus 2 plus the natural log of x minus 3, same as what we talked about in 4. But these two that end up on the bottom get minuses. So minus the natural log of x plus 1 minus the natural log of x plus 5. So that's that quotient property. And then when you go about taking the derivative, again, 1 over y times y prime on that left side. Here I just have 1 over x minus 2 plus 1 over x minus 3 minus 1 over x plus 1 minus 1 over x plus 5. And you could get some nasty common denominator and put all this back together if you needed to. But I'm just showing you the general technique now. And then I would multiply both sides by y. So y prime would equal y times all of that. And then if I plug back in for y, that fraction I started with, I have x minus 2, x minus 3 over x plus 1, x plus 5. And then I can fill in that parentheses. And that is my derivative with everything plugged in. And, you know, they may have simplified this more. Like I said, they may have gotten common denominator, put this together, canceled things out. You're probably going to look at this in a multiple choice situation, so you just have to be able to use legal algebra moves to see if your answer matches one of their answers. But that concludes this lesson.